Okay, we talked about 3.1, 3.2, but we didn't finish 3.2 last time. The last thing we talked about was the real zeros of polynomial function. When it asks you the real zeros of a polynomial p, it's asking you the solutions of this polynomial equation px equal to 0. You need to solve this equation and get the solutions. And those solutions are called the real zeros of the polynomial if they are real solutions, okay? All right. Sometimes you may get complex solutions, and they are called complex zeros, okay? But that's what it means by real zero. All right, so let's just do an important theorem now. In algebra, it's called the intermediate value theorem. Okay, so it says if polynomial p is polynomial function, and if p of a is not equal to p of b for a less than b. Okay, so you got 2 points on the curve of the polynomial function. If you draw the graph of the polynomial function, you pick up 2 points on the graph with not the same height. Okay, p of a not equal to p of b. So one is a little higher, one is a little low of those 2 points on the curve. Then it says the polynomial p takes on every value between pa and pb in the interval from a to b. Okay, because polynomial, any polynomial is continuous. So if you draw the graph, it's a continuous curve. Then when you draw the curve between a and b for this polynomial, then it takes all the value from pa to pb. Okay, because it's continuous. So I guess we're going to do one example so that you understand what it means for this theorem. In this problem, we need to show that the polynomial p of x equal to x cubed minus x minus 2 has a 0 between 1 and 2. Okay. So as I said, when it says the 0 of polynomial, it means you need to solve this polynomial equation of px equal to 0 and see what the solutions are. Then they are called zeros of the polynomial. So we need to solve a polynomial equation with degree 3, a cubic equation. X cubed minus x minus 2 equal to 0, and it is hard to solve, okay? And it doesn't have integer solutions actually. But then, you can still have some idea where the solution is, even though you cannot solve it easily. So this question is asking you to show that the polynomial equation p of x equal to 0 has a solution between 1 and 2. So x may be equal to 1.5 or something. That's a solution, but it's a polynomial equation p of x equal to 0. 1.6 or 1.4, we don't know. But we know there is a solution for this polynomial equation x cubed minus x minus 2 equal to 0. And the solution will be between 1 and 2. Okay. So so what you do, you just pick up 2 points on the curve. We're going to pick x equal to 1, x equal to 2 on the curve. So, and then evaluate the function value at those two points. So p of 1 equal to 1 cubed minus 1 minus 2. Just plug in 1 for x and p. And 1 cubed is 1, so you get 1 minus 1 minus 2, which is negative 2, so that's negative. So this point is below the x-axis on the graph, right? And then let's just evaluate the polynomial function at x equal to 2. So plug in 2 for x. For the polynomial, then we got p of 2 equal to 2 cubed minus 2 and minus 2. 2 cubed is 8, so we get 8 minus 2, which is 4, and that's positive. So this point will be above the x-axis because p of 2 is greater than 0. So then we got 2 points on the curve. One is at x equal to 1, and one is at x equal to 2. So you can see this graph on the right, those 2 points. So we got 1, -2, x equal to 1, y equal to -2 as 1 point below the x-axis. And the other point, 2, x equal to 2, y equal to 4. Okay, 2, 4. That's above the x-axis. Okay, so the curve just crossed the x-axis in between x equal to 1 and x equal to 2, right? Because it's continuous. And that's because of the intermediate theorem, P takes on every value between P1 and P2 in the interval from x equal to 1 and x equal to 2. Okay, so it will take the value 0, P will take the value 0 since 0 is between -2 and 4. Okay, in somewhere in the interval from 1 to 2, right? And that's the 0 we're talking about. Okay, you can see the graph, that's actually the case. We don't know what exactly where it is, but it has to be between 1 and 2, right? So then we conclude that Px has a 0 between 1 and 2. Any questions about this example? No question. Then we go to the next page. Okay, let's talk about real zeros, X intercepts, and the factors for polynomial functions. So it turns out they are very closely related. Okay, and when we say the following 3 things, there are equivalent statement. Okay, so for example, if you say x minus c is a factor of a polynomial p of x, that means x equal to c is a real solution of the equation p of x equal to 0, because when you solve the polynomial equation p of x equal to 0, you factor px on the left, and you get a factor of x minus c. So then you set x minus c equal to x minus c equal to 0, and you get x equal to c as a solution to this equation, right? But that's also mean that x is a real 0 of p, because x equal to c is a solution, okay, a real solution actually of the equation px equal to 0. Equivalent, we can say x equal to c is a real 0 of p. That's how what it means by a 0 of p. You solve the equation p of x equal to 0, and you get solution x equal to c. Then that c is a real 0 of p, right? Okay. Any questions about this? Nope. And then we have one more slide for this section. Even and odd powers of x minus c theorem. Okay, so that's another thing that will help us to draw the graph polynomial when it is not so easy to graph the function. Okay, so it says, this theorem says, if p of x has x minus c as factor k times k greater than 0, of course. So x minus, when you factor px, you get a factor x minus c, and it appears k times, like 2 times. So for example, if you can factor p of x, you can factor x minus 1, and factor again, you get another factor of x minus 1 for the reduced polynomial. Then you actually get the x minus 1 as a factor 2 times, right? Okay. So if that's the case, then the graph of p will intersect but not cross x-axis at c0. Okay, we know And this C0 is actually a x-intercept of the polynomial. All right. If we plug in C for P, for x in P, you get 0, right? Because x minus E is a factor of P. So P of C equal to 0. So that means C0 is a x-intercept of this curve. Okay, so when if k is even, then the curve of P will intersect but not cross the x-axis at C0. Okay, so in other words, the x-axis is the tangent line to this curve. Okay, so the curve intersect but not cross. Okay, so the curve just lies on the same side, even above or below, either above or below the x-axis. So it does not cross x-axis at this intersection, right? So that's one case. And if k is odd, then the graph of P of x will cross the x-axis at the point C0. It will cross. Okay, so it crosses the x-axis from positive to negative or from negative to positive. Okay, so those are the x-intercepts. Okay, there are two different types of x-intercepts for the curve. Okay, let me just explain this then from an example. For example, we want to scale the graph with polynomial p equal to x plus 3 times x minus 2 squared times x minus 4 cubed. Okay, so we can find the x-intercepts easily. Or you can say, px has x plus 3 as a factor one time, because the exponent of x plus 3 is 1 if it doesn't enter anything there. X minus 2 as a factor for p 2 times. It's x minus 2 squared. And x minus 4 as a factor 3 times. So x minus 4 cubed when you factor p. Okay, according to this theorem, even an odd powers of x minus c theorem, the graph of p of x intersects but does not across the x-axis at 2, 0. Okay. So if you put px to solve px equal to 0, you get 3 solutions: x plus 3 equal to 0, x minus 2 equal to 0, x minus 4 equal to 0. Those are the x-intercepts of the graph of p. So so one of the solutions is x equal to 2. You got 3 solutions: negative 3, 2, and 4, right? So 2 is one of the solutions, or 2, 0 is a x-intercept of this curve. Because the power of x minus 2 is 2, that's even. According to the theorem, the graph will be tangent to the x-axis. It does not cross the x-axis, but it does have a tangent point with the x-axis at 2, 0. All right. You can see the graph. At 2, 0, the curve actually lies below the x-axis, but it is tangent to the x-axis at a point, right? We have two other x-intercepts. If you solve for x plus 3 equal to 0, you get x negative 3, and if you solve x minus 4 equal to 0, you get x equal to 4. So negative 3 and 4. So these two points are negative 3, 0, and 4, 0. X equal to negative 3, y equal to 0, and x equal to 4, y equal to 0, right? And the exponent for x plus 3 is 1, and the exponent for x minus 4 is 3, so they are odd. So for these 2 points, the curve does cross the x-axis, because the exponent for each of those 2 factors is odd. So the curve goes from positive to negative or negative to positive at those 2 points. So the graph of px crosses x-axis at negative 3, 0 and 4, 0. So you can see the graph, negative 3, 0 on the left, the curve crosses the x-axis, and on the right at 4, 0, the curve also crosses the x-axis. Okay, so then at least you can sketch the graph with a rough estimation of this shape, what it looks like, So that's the end of this section 3.2, and we just finished the section. Any questions for 3.2? So you can see we got a bunch of things to talk about, the zeros of polynomials and a couple of theorems. So things become a little more complicated now. We discussed pretty much in detail about this zeros of polynomials, right? Okay, so no question. Then we go to the next section, 3.3. Okay, 3.3 is zeros of polynomial functions. So we just continue with the topic of zeros of polynomial functions, and let's just have a general discussion about the zeros, and we will have emphasize on these zeros and this in this whole chapter. Okay, this essentially we want to solve the polynomial equation P of x equal to 0, and that's also called the zero of a polynomial, right? So the question is actually, how do we factor the polynomial? How do we solve this polynomial equation? Okay, let's just start from the basic terms. Multiple zeros of a polynomial function. We already had one example in last section, but let's just see one more example. Okay, so let's define the multiplicity of a polynomial of 0, of polynomial p. So if polynomial p of x has x minus r as a factor k times, as we did in the previous example, then r is the 0 of multiplicity k of px. Okay, the exponent of the factor. For example, let's say p of x equal to minus 5 squared times x plus 2 cubed times x plus 4. So then we have three factors, x minus 5, x plus 2, x plus 4. Or we can solve this equation easily, x equal to 0, and we got three solutions, 5, negative 2, and the negative 4. If we set the x minus 5 equal to 0, you get 5 for x. If you set the x plus 2 equal to 0, you get the x equal to negative 2. If you set the x plus 4 equal to 0, you get the x equal to negative 4, x equal to negative 4. So we got three zeros, 5, negative 2, and negative 4. And each zero has a multiplicity corresponding to the power of the factor. So for example, 5 has 0 of multiplicity 2 of p of x, because you got x minus 5 squared. The exponent is 2. And negative 2 has a 0 multiplicity 3 of the polynomial p, because we got the exponent 3 for x plus 2. And negative 4 is just a 0 multiplicity 1 of p, because the exponent for x plus 4 is 1. Okay, so one of the important conclusions is a polynomial p of degree n. Okay, remember what does it mean? Degree of polynomial, it means the highest power term of the polynomial. If you multiply out, for example, in this problem, if we multiply out the polynomial p with all those three factors, with different multiplicities, then you're going to get a bunch of terms with different powers of x, right? And the highest term, highest degree term, you know, is called the leading term, and the highest power is called the degree of the polynomial. Okay, so a polynomial p of degree n has at most n zeros with multiplicity counted. So what it says in this statement is if you have, for example, cubic equation, x like x cubed minus x minus 2 equal to 0, like we had last time, and then it says if you say that equal to 0, you solve the cubic equation, you can get at most 3 zeros, or at most 3 solutions. So a cubic equation has at most 3 solutions, and some of them may be identical. So you may actually end up with only 2 solutions. Okay, and if you consider quadratic equation, then it's easy to understand. So quadratic equation is a polynomial of degree 2 because the highest power of the polynomial is x squared. So it has power term. And then, so n equal to 2 in that case, and then it has at most 2 zeros. If you solve a quadratic equation, you can get at most 2 solutions, right? You cannot get 3 solutions from quadratic equation. And sometimes these 2 solutions may be identical. You end up with only 1 solution in that case, right? We have this kind of cases. The quadratic equation may end up with only 1 solution, or we can say repeated solution or identical solution. Okay, so and that means the solution has a multiplicity 2 or 0, or 0 has a multiplicity 2, right? Okay, so of course for a linear equation you only have the degree is 1 because the highest power term is the x. The exponent of x is 1, so it has at most 1 0. So when you solve a linear equation, you can only get the 1 solution, right? And so in general, for example, if you try to solve a polynomial with degree 10, for example, that means the highest power term of the polynomial is x to the 10. So you get a bunch of terms, but you start from x to 10 with some coefficient for each term. Then you solve that polynomial equation, you can get most 10 solutions. And you may get the number of solutions less than that. You may get only 7 solutions, for example, because some of them may be just identical or has some multiplicity greater than 1, right? Okay, so that's one thing we want to know first. All right, so I hope you can read the words in here, the small. Okay, we have another theorem comes up. It's called the rational zero theorem. All right, so now, as I said, for a polynomial with degree n, we have at the most n zeros. Then the question is, how do we solve this equation? Can we have some easy to even try to solve the polynomial equation, especially for polynomial equation with high degrees, like degree 3, 4, or 5? Can we at least get 1 solution in some way? So this rational zero theorem just tells us that it is possible to find a rational zero. That means the solution of the polynomial equation is a rational number. So it's possible to get some rational zero for this polynomial from the coefficients of the polynomial if all the coefficients of the polynomials are integers. Okay. So what it means is, you have a polynomial p equals a n x n plus a minus 1 x to the minus 1 plus everything else down to a1x plus a0. So this is called the degree of the polynomial, as we said. And those numbers, a n minus 1, a1, a2, all of those numbers with the power function, I call it the coefficients. Okay, they are constants. So if all of these numbers, a and a minus 1, a1, a0, all of those, there may be some terms in between. All of those coefficients are integer. Okay, so we talk about this case, special case. So this polynomial p has all coefficients integers. All right, all of them are integers. And then we can, possibly find some rational zeros or rational solution for this polynomial equation px equal to 0. And how do you, determine those? How do you find those possible rational zeros or rational solutions? You just factor the first number an, the coefficient for the leading term, and the last term a0, okay, the constant term. You factor those two numbers, and we call p is factor of a0. Okay, you factor the last number, you get a bunch of factors, and p is one of the factors of that number. And then you factor the first number an, and you get a bunch of factors, and q is the factor of an. Okay, and then what we do is just divide p by q. Okay, divide those two factors from a0 and a, and then that's possibly a rational zero of px. So it is possibly a solution to this polynomial equation px equal to 0. All right. So that looks a little confusing, isn't it? So let's just do one example and see. You can see what it means in here. Okay. In this example, we need to find all possible rational zeros of the polynomial p equals 4x to the fourth plus x cubed minus 40x squared plus 38x plus 12. So this polynomial, with degree 4. So we want to solve this polynomial equation px equals 0, or 4x to the fourth plus x cubed minus 40x squared plus 30x plus 12 equal to 0. How do you solve this equation? We're going to start from this rational zero theorem. So in this polynomial, the leading term is 4x to the fourth, and the leading coefficient is 4, and we call it an. And the constant term is 12, we call it a0. Okay. Then you factor both numbers. So for example, you factor 12 constant. Then you're going to get the positive or negative 1, positive negative 2, positive negative 3, positive negative 4, positive negative 6, positive or negative 12. So those are all the integer factors, all the factors of 0, 12. And then you factor the number 4. You get the plus or minus 1, positive or negative 2, positive negative 4. So you get 6 factors for the leading 4. And then you just divide the factors of p by the factors of q. Okay, so we got how many factors for p and for a0? 1, 2, 3, 4, 5, 6. So we got 12 if you count both positive and negative. The 12 factors for A0, and we got 6 factors for AN. So then you just divide those 12 factors of A0 by each of those 6 factors of AN. Okay, so for example, we just do it one by one. So if you pick a positive or negative 1 from the factor of A0, 12, divide by each of the factors of AN, which are, positive, negative 1, 2, and 4. So 1 over 1 is just a 1. So we get a positive, negative 1 for Q, right? Then 1 divided by plus minus 2, so you get the positive, negative 2, 1/2, right? And plus minus 1 over plus minus 4, you get the plus minus 1/4. Okay. And then you go to the next factor of 12, plus minus 2. And then divide that by each of the factors of AN. So you do 2 by 1, you get 2, so plus or minus. And 2 by 2, you get 1. So that's plus minus 1, but we already listed it in the first place, so we don't have to repeat it. And then 2 over 4 is 1/2 if you reduce it, so that's plus minus 1/2. We also had it in the second place, so we don't have to write again. And then you do 3 over 1, you get 3 with plus minus. 3 over 2, you get the 3/2 plus minus, and 3 over 4, you get plus 5 plus minus 3/4, right? And then you go to 4 for the factor of 12, A0. 4 over 1 is 4, so you get plus minus 4, and 4 over 2 is 2, so you get plus minus 2, but that's already listed before, so we don't have to write. And then 4 by 4 is 1, so you get plus minus 1, but that's also included before, so we don't have to write again. And then you do the 6. 6 over 1, you get 6, so you get plus minus 6. And then 6 over 2, you get a 3 with plus minus. That's already listed before. And 6 over 4 is 3 over 2. If you reduce it, and that's also listed before. So we don't have to write again. And then you get a 12 over 1. You got 12, so you get plus minus 12. And the 12 over 2, you get a 6 plus or minus 6. But we already wrote it. So we don't have to write again. And then 12 over 4 is 3, so you get plus minus 3. That's already included before also. So, and then we don't have to write again. So we get all of those possible zeros of the polynomial P. Okay, so that's what we do. We get a bunch of them. How many do we have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. With plus and minus, we got 20. So we got the possible rational zeros of P. They can only be from those 20 numbers. Okay, if you solve this polynomial equation, px equal to 0, if you have rational zeros, if you have rational solutions for that equation, then they must be for 20 numbers. But we already know this polynomial equation, this polynomial only has degree 4, x to the 4th, right? Degree 4. So it has at most 4 solutions if we solve this equation. So obviously we got the many more possible rational zeros of the polynomial than needed. That means most of them, of those 20 numbers, will not be solutions of the polynomial. You might get a few of them, maybe 1 or 2, for example. Or maybe 4 of them, or all of them are rational zeros. But you could also end up with none of them or zeros of polynomial. If you solve this equation, maybe all of the solutions are irrational, for example, and that's possible. So that's why we said those are the possible rational zeros. of the polynomial, and you might not have nothing. You might not get nothing from those numbers. Okay, so that's the first thing we want to talk. Any questions at this point? No question. Let's just go to the next thing. Okay, so things get a little weird now. Okay. So we just discussed how we try to find the rational zeros of polynomial to, solve a polynomial equation with rational solutions by the method we just did on the previous page. Please do not move the indicator. Please do not move your hand on the on the what on my slide. I don't know who is doing that. Okay. So the next thing is called upper bounds for real zeros of a polynomial and the lower bounds. Okay, let's just talk about upper bounds for real zeros of a polynomial p equal to a and x n plus a minus 1 x n plus 1 plus other terms down to a1 x plus a0. So this is a general polynomial with degree n. Okay, it turns out that we can actually tell, the upper bounds and lower bounds of the polynomial, zeros of the polynomial. When you try to solve a polynomial equation, you can actually tell the roots, the solutions will be between some numbers. You can determine that upper bound and the lower bound. For example, if you try to solve a polynomial equation, you may find all the solutions must be less than 3 and greater than -2. And then we can actually do that. But, what exactly the bounds are, we have to figure out by doing the syntactic division. Okay, so in here it says, how do we determine upper bounds for the real zeros of a polynomial? So let's say we got the positive number b, and the leading coefficient of this polynomial a n is positive. Okay, so then b is an upper bound for real zero of p if none of the numbers in the bottom row of the syntactic division is negative. All right, so you just do the syntactic division of the polynomial with this number b, and then you look at the bottom row of this syntactic division. If none of the numbers in the bottom row is negative, then we know this number b is an upper bound for real zeros of p. Now, in other words, all the solutions of this polynomial equation p equal to 0 have to be less than or equal to b, this number b. So that's the case when the leading coefficient a and a is positive. What if the leading coefficient a and is negative? Then you also do this division for the polynomial with positive number b. Okay. And then this time you look at bottom row. If none of the numbers in the bottom row of the syntactic division is positive, then we can claim b is upper bound for the real zeros of p. Okay. So again, you can say that all the solution of this polynomial equation will be less than or equal to this number b if none of the numbers in the bottom row of the syntactic division is positive. They could be 0 or negative. So that's for the case a n less than 0. The leading coefficient of the polynomial is less than 0. Okay, so let's do one example and see how we use this theorem to figure out the upper bounds of real zeros of polynomial. So we need to find the smallest positive integer upper bound for real zeros of the polynomial p equals 2x cubed plus 7x squared minus 4x minus 14. So we try to solve this polynomial equation px equal to 0, and we want to find the smallest positive integer upper bound. So we want the the upper bound for the solutions, but the smallest. Okay. So what we do? We're gonna start from b equal to 1 because b is a positive number in the theorem. So we only use the numbers b positive numbers, and the smallest integer positive integer is 1. Start from 1. Do the syntactic division. And so if you do that, if you still remember how to do it, you put all the coefficients 2, 7, -4, and -14 on a row, and then put one outside, and then do syntactic division. So move the first two down, multiply 1 by 2 equal to 2, and then put under 7. So that's multiply up, and then 7 plus 2 equal 9. So let's add down, and then you multiply 1 with 9 equal 9. Put it -4. So that's multiply up. -4 plus 9 equal 5, and then 1 plus 5 is 5. You get we put it down -14, so it's a multiply up. And -14 plus 1 is -9. So you can 9. So, and in this case, the leading coefficient n equals 2, so that's positive. And we got one negative number in the bottom row. So that means 1 is not a upper bound for the real zeros of this polynomial. So that means there are some solutions greater than 1 if you solve this polynomial equation. So then let's increase to 2 and see what happens. Do the syntactic again. So move 2 further, move 2 down again, and then multiply 2 by 2, you get 4. And put it down to 7, you get, and then you plus, add 4 and 7, you get 11. And then multiply 2 by 11. You need to put it in, under -4, so that's up, multiply up. And then you add -4 with 22, you get a positive. And then you multiply 2 with 18, you get 36, and multiply up, put below -14, and add -14 with 36, you get a 22. You get 22. So you can see all the numbers at the bottom row of the syntactic division are positive. So then, according to the theorem, we can say 2. So b equal to 2 is a upper for real zeros of this polynomial, right? And it is indeed the smallest positive integer upper bound because 1 is not. So 2 is the smallest positive integer upper bound, right? Of course, 3 will be also positive integer upper bound, but it's not the smallest. 2 is the smallest. Okay. Any questions for this example?